Okay, here is the problem we're trying to solve. We're told that there's a function, p of t, which is the performance level. The units of this are in units per minute, so it's people performing some job where they're producing something, and the performance is units produced per minute. M is going to represent the maximum performance, and K is going to be a positive constant. And in those conditions, we're given the following differential equation. dp dt equals km minus p of t. This is a model for learning. How does your performance level change over time? K and M are both going to be positive, so if you do a little thinking on this, what you see is that when you have almost no performance level, when you're just starting out, you can learn rather quickly, but the closest you get to your peak performance, the slower your learning becomes. It's harder and harder to get that, acquire new skills as you go on. We're also given some information, some values of the function. P of 0 is 0, P of 1 is 11, P of 2 is 14. And our goal here is to find the maximum performance. In other words, find M. Okay? So here is our differential equation. And our first step is going to be to recognize this as a separable equation. And so I can divide m minus p to the other side. And we're going to get dp over m minus p is equal to k dt. So we're using that separable equation formula that we've seen, and we're going to integrate both sides. Okay. Here we have a, pardon me, you can do a substitution here, and you'll find that the antiderivative is going to be the negative natural log of the absolute value of m minus p. And over here, we're getting kt plus a constant of integration. Remember that k and m are just constants in terms of these integrals. Okay. So I'm going to take the negative to the other side. Negative kt. I'm not going to worry about multiplying an arbitrary constant by a negative because it's still an arbitrary constant. And then I can use the definition of the exponential or the natural log to write that the absolute value of m minus p is equal to e to the negative kt plus c. Okay, so let's take this expression up here. And what I can do, let me do one more thing here. I can use rules of exponents to write this, e to the negative kt times e to the c. Oh, this was written poorly. This is part of the exponent. So we would be adding these exponents, right? Moving backwards, you know this rule that way. I'm just doing it in the other direction. And what this lets us do is rewrite the right-hand side as a e to the negative kt, right? What I've done is say, well, c is an arbitrary number, e to an arbitrary number is just an arbitrary number. Okay. I'm also going to use this opportunity to drop the absolute value. We will use the given information here to find out the value for a, and whether it's positive or negative will shake out from this, and so that plus or minus from the absolute value is kind of being absorbed by that arbitrary constant there. Okay. Now I'm going to rearrange this algebraically, and what I can write is my function p is equal to m minus a e to the negative kt. So there's our general equation solving this differential equation. And now we're going to use the information over here to get the values for these constants, m, a, and k. So the first thing I'm going to do is use p of 0 equals 0. P of 0 will be m minus a. E to the 0 is just 1, and this is equal to 0, so I have the equation m minus a equals 0, which you can solve to see that m equals a. So now my equation looks like m minus m e to the negative kt, or maybe I might want to write this as m times 1 minus e to the negative kt. Okay, so we've got one of our constants, or we've gotten rid of one. I guess we shouldn't say we have it, we just know that it's equal to the other one, so now we're down to two constants we need to figure out, k and m. So I'm going to use this other bit of information, and all I'm going to do is write these expressions. P of 1 equals 11 can be rewritten as, well, P of 1 is just m times 1 minus e to the negative k. That's equal to 11. And P of 2 equals 14 is m times 1 minus e to the negative 2k is equal to 14. Okay. So now I've got to solve these two equations. Let's take, it doesn't really matter which way we go. I'm going to take this equation with the 14 and divide it by the equation over there. What I'm using is this fact. A equals B. If A equals B and C equals D, then A over C is equal to B over D. This is true as long as C and D are not 0, as long as we're not dividing by 0. So if we have two sets of equal things, their ratios are going to be equal, right, in this way. So in this case, I know they're not equal to 0 because the only way 1 minus e to the negative k or 1 minus e to the negative 2k is equal to 0 is if k is 0, because then we'd have 1 minus 1, and 1 minus 1 is 0. But we know that k is greater than 0. So this part this won't ever be 0, m can't be 0. And we also know that they're both equal to constant numbers, so we don't have to worry about these zeros here. All right, so we divide. We'll get, let's move up here. I'm going to get m over 1 minus e to the negative k equals 11 divided by m over 1 minus e to the negative 2k over 14. So I guess I divided the opposite of what I said I would do, but it won't really matter. So what happens here that's nice is the m's cancel. Okay, and I have this equation here. I'm just going to remove my fractions by multiplying things around. So on this side I'll have 14 times 1 minus e to the negative k equals 11 times 1 minus e to the negative 2k. Then I can write, let's multiply these out. I'll get 14 minus 14 e to the negative k equals 11 minus 11 e to the negative 2k. Do some rearranging and I get 11 e to the negative 2k minus 14 e to the negative k plus 3 equals 0. Okay, so I just moved everything over to the left-hand side. And let's do a little factoring. I'm going to rewrite this negative 14 as minus 11 e to the negative k minus 3 e to the negative k plus 3 equals 0. I can factor the first one by taking out an 11e to the negative k, gives me an e to the negative k minus 1. Here I can factor out a negative 3, I got e to the negative k minus 1 equals 0. Now I can factor out this binomial from each. I get e to the negative k minus 1 times 11 e to the negative k minus 3 equals 0. And so if these two things multiply to be 0, it means that e to the negative k minus 1 equals 0, or 11e to the negative k minus 3 equals 0. Right? Well, this one has only one solution. E to the negative k minus 1 equals 0 if this thing is 1, and that's only 1 if k is 0, but we already said that can't happen. K has got to be positive. So this one doesn't give us a solution in our situation. Okay. So let's focus on this one. I can rewrite this as e to the negative k equals 3 over 11. And that's going to give us negative k equals the natural log of 3 over 11. But actually, I think this will be even more useful. We'll see in just a second. So, remember what our job is. Our job is to find m. right? We want to find out what m is. So now that I have an expression for e to the negative k, I have a number that I can put in here. I can take this equation, m times 1 minus e to the negative k equals 11, and just put in 3/11, right? Which is m times, well, 11/11 minus 3/11 is 8/11. And then if I multiply both sides by 11/8, I get m equals 121/8. And there's the value for m. That's the maximum performance level in this situation. Here is a look at the full thing.